All right, hi all, this is Mr. Yeager. Moving on with our next topic, basically on how we're actually going to now involve some equations with this, a bit more, more of the physics kinematic equations that are going to be used throughout this unit and throughout basically throughout the year. If this is for AP Physics, we're continuing Unit 1 still, continuing our kinematic unit. If we are looking at this from regular physics, this is our new unit. This is the introduction to the new unit. Okay? So we're looking at measuring motion a bit more now. Again, we've already done it with graphs. Okay? We've already done it with motion dot diagrams. And now we've also been given a few formulas. Speed is distance over time. Average velocity is total displacement over time. All right, average speed is total distance over time. Okay, what we are we also introduced acceleration as well. Okay, final minus initial velocity over time. That is the only true kinematic formula that will continue into this next unit. The other ones are important to remember: speed, average velocity, average speed. But we are going to be getting a little bit more specific now, rather than looking at it from an average standpoint. Okay, so for this particular unit, our goals will be to understand the kinematic equations. Again, if we're looking at AP, we're still in Unit 1. But still, our goals would be, we want to understand these kinematic equations. We want to use the kinematic equations for linear motion, okay? Motion in a straight line. And we're going to use these equations to introduce free fall problems. Problems where it's not just a car or a person running straight back and forth, but now an object that's falling through the air or being thrown up straight into the air. Okay, not at somebody. We're not playing catch yet. We're basically somebody has a ball in their hand throwing straight up, but that'll be a separate video. Okay, so we will involve some math here. Okay, and so I am going to obviously try to push an approach to these problems, because again, certain people really struggle with these at times. But we got to start learning these formulas. We have to feel like, I would say, almost start memorizing these formulas once we start using them quite a few times. Okay, you always have a formula sheet, but we need to be feeling good, going, okay, I know what equation the one they're talking about here is. Okay, so when we are doing these problems, I'm going to tell you, identify what you have. Okay, I know some people immediately rush to start plugging in numbers. Okay, identify what you have. Identify what you have. Okay, identify what you're solving for. I mean, again, if you're good at math, you're already doing this. Just take your time. Don't make really bad mistakes. Okay, and then match the appropriate equation based on what you have. There are 3 equations. Okay, 4 technically. That I'll introduce a 4th that's just not used that often in AP Physics. It's really only 3. But you're gonna see each equation obviously has specific values with it. Obviously, some will show up in each equation, but there'll be also something missing in each. So we'll be able to sit there and go, okay, I can't use this equation for this problem, but I can use this one. Okay, so we want to match it up and then obviously solve. All right. So for kinematics, this is actually a very important point, because this is going to be something that comes up later when we get to energy, which is one of the more difficult units for people. Kinematic equations will be used in problems where we are solving with a constant acceleration. In other words, one acceleration. All right? We can only do these problems if there's one acceleration. It can be 0. There can be no acceleration. You can use the formulas to solve the problem. But we cannot do a problem. What's basically going to happen is we can only have one acceleration. If there's a second acceleration that occurs, you're going to have to do a completely different equation. Like, you can use the kinematic equations, but you're going to have to use it for that acceleration, then solve it again with a different acceleration, then solve it again for a third acceleration, and so forth. So we're trying to keep this simplified. These are problems where the object either has 0 acceleration or a single value acceleration. Okay, one acceleration. All right, and so here are the different variables we'll be playing with during these kinematic problems. Okay, I have this written more for regular physics, so I'm going to make sure it's clear for AP Physics. The only big difference, and the AP committee actually doesn't care that much, but on a formula sheet for AP, displacement is delta x. Displacement is delta x, and then v, instead of vi, we say v naught, the v little 0 there. Okay, that would be v initial. The other three are the same, okay? So these are the same thing, all right? And it's actually, for me, and again, the AP committee, they would accept either one, understanding that you know what these symbols basically mean, all right? But on a formula sheet, we want to make sure you understand what they represent as well. In regular physics, same thing. If you want to use either one, that's fine. But this is what's going to be involved in these. It doesn't mean that's going to show up in every equation, but we're going to have displacement, initial velocity, final velocity, acceleration, and time. For these problems as well, we are basically looking at the object going one direction the whole time, essentially. Okay, going one direction. All right. There will be ones that we can talk about where maybe it goes up and down, but then again, we'll be able to solve for that. I mean, it's still essentially only going one direction. It depends on what you're looking at from beginning to end. Like, where are you starting the problem? Where are you ending the problem? Okay. But these are going to be your 5 possible variables, all right, with the units involved with it. All right. So, if you would notice real quick from that last slide, all those variables are vector quantities except for time. That means displacement, acceleration, final initial velocity. All these variables except for time can be positive or negative in the equation. So you do have to pay attention to the direction that you are going. Again, the nice thing is we are primarily going to go only one direction at a time. So displacement and distance are even the same. We're not going to have to worry about that confusion anymore. Okay? There you go. All variables can be positive or negative. All right. So the kinematic equations are going to be on the next slide. All right. Things I want you to notice. All right. What variables are in each equation? All right. What variable is missing in each equation? There's going to be one variable missing in each equation. Okay. And so here we go. These are your big 4 equations. Okay. The big 4. All right. With the second one being the one that's not as important in AP Physics. So that one's not as important. I'll go and number these differently. I'll circle them. The first equation, the second equation, and its small variation underneath of it, and this bottom equation, these are your AP primary equations you'll be using. This second one there, I mean, if you can remember it, you can definitely try to use that some. The only thing I'll be careful about with this is related to average velocity. So that's why we try to avoid that some in AP Physics. So anyway, here's your equations. Again, you can match them up with the ones on your formula sheet. Again, these can be delta x's. Okay, these are delta x's, so same thing there. Okay, VI's are V naughts. So just to make sure we're aware of that, I'm going to erase everything here. Okay. But these are your main equations, and so you can see what variables in each particular equation. So let's go through and go, okay, well, what variable's missing? Okay, what's the missing variable? All right, in the first equation, the missing variable is displacement. So if you have displacement, don't use the first equation, okay? And again, what the first equation is showing you, this is your acceleration formula, just written differently. It's the same thing as this, Vf minus V naught over T, okay? That's the exact same equation, which we've been talking about. So we actually know number 1 already. Number 2, all right, if we happen to be using this one, especially in regular physics, you can see that we don't have acceleration in that problem. In the third one here, we don't have final velocity. And in the last one, the one at the very bottom, sorry, this one up here, okay, we are missing time. Okay, we're missing time in that equation. All right. Just to kind of see what you mean, what's this saying? It says it right here. This is probably like one of the most important equations. I don't want to sit there and be like, you're going to use this more often than not. The bottom 2 are used quite a bit in AP. This first one is sort of simple enough that I think everybody just basically gets it. But the third and fourth one, the third one, we have a variation to it that's going to happen quite a bit. All right. You can see it's delta x d equals VIT, V naught t plus 1/2 AT squared. Initial velocity in a lot of problems, will be 0. If V naught equals 0, this whole thing goes to 0, and so delta x equals 1/2 AT squared. This would be the formula if you want to figure out how far something will go, and you know the acceleration, it starts at rest, and it accelerates for 5 seconds at 10 meters per second squared. That would be your formula, okay? I think sometimes people sit there and go, oh, I don't have initial velocity. You're going to have to read between the lines. You're going to have to read the problems carefully. If the problem says the object starts at rest, you know you have an initial velocity of 0. Okay, so those are your big equations. All right, so here's the breakdown of all that. What I just said. Again, be aware, especially for AP students, delta x is d and vi is v naught. Okay, they will be used more often on the AP test. All right. So again, I made that table because the biggest problem I usually have with students early on is they go, I just don't know where to go. I don't know what formula to use. I'm confused. I'm lost. Okay. Well, first usually I just say, go back and read the problem. Okay. Relax and read the problem. All right. At this time, I'm expecting you that you already know how to identify acceleration, how to identify velocity, how to identify displacement. If you don't know that, you need to go back to Unit 1 and really kind of, or, the initial lectures and really make sure you go over those some because you're behind. Okay? But if, what formula should we use? I get it, it's new, okay, but we just need to find it out. Okay? The table there is meant to help you kind of go through and go, okay, which equation should I use? All right, and then you can base it on either what is given to you or what is missing. Okay, and you can then go, oh, I need to use this particular equation. All right. So how do we solve a problem? Read the problem carefully. Try to visualize. Make a sketch. Okay. I'm going to tell you, the more you draw, and especially next, when we get the forces eventually, and even with projectiles soon, you're going to need to draw some. You got to see it to really understand what's going on. Especially if you're sitting there making mistakes constantly with the direction of the velocity and the direction of the acceleration. Are you getting it wrong because you made the acceleration positive when it should be negative? If you sketch it out, if you draw little arrows for things, you can hopefully understand what the problem is trying to say. Define your variables, obviously determine what you have. Okay? Write out knowns and unknowns. Okay? Decide which formula you can then go to, and then solve. Okay? That's what we're looking for. Plug in the numbers and solve. All right? Obviously, you want to check your answers. All right? Do they make sense? All right? Do you have the right units and everything? Okay? So, if we do just a couple practice here, and I'm going to do another video of more practice, let's try to go through this. Actually, I think all this is already done for us, so let's just kind of go through. A race car starts at rest and accelerates at a constant acceleration of 0.75, positive 0.75 meters per second squared for 10 seconds. What is the rider's displacement during this time? Okay, so what do we have? Okay, let's go. You have the initial velocity. It doesn't say 0, but it does say that you are at rest. Okay? Rest means 0 velocity. Okay? Rest means 0 velocity. You have acceleration, you have time. You're trying to solve for your displacement, and you don't have the final velocity. So what equation should we go to? If you go back and look through all those equations, hopefully you wrote them down. Okay? You're trying to find the equation where it's displacement. I mean, you can look at sit there and go, if you do have initial velocity, but it's going to be eliminated. Acceleration time, no VF. That equation you're going to use is the d equals VIT plus 1/2 AT squared formula, or x equals V naught t plus 1/2 AT squared formula. We have all of those things. Okay? You can go ahead and plug it on in. Technically, do I need to write out 0 times 10? No. I mean, you could literally just eliminate this part. Okay? And you go, okay, this problem is just 1/2 times 0.75 times 10 squared. Please make sure you time it. Okay, that's another little thing I see some people do. This is only squaring t. It's only t squared. 1/2 a is not squared. So make sure you only square the time. Okay, I've seen other people. The two common mistakes are people don't square the time or they square everything. Okay, so obviously follow the formula as it's given to you. All right. So here's another one, starting from rest. Okay, that's just an extremely common situation, and we like to start from rest. Okay, a race car moves 100 meters in the first 5 seconds of uniform acceleration. What is the car's acceleration? Okay, you have again initial velocity 0. You have distance 100 meters and time 5 seconds. You're trying to find a. Again, you don't have final velocity, so guess what? You can go ahead and use this formula again. All right. Could you possibly use a different formula and find final velocity? Sure, you can find final velocity and then do 2 steps. That's fine. I'm just trying to always do it the fastest way, the way that I have an equation and it can solve for immediately. This one, Again, I can eliminate VIT, and it's just D equals 1 half AT squared. I can solve for that, okay? And my answer should come out to 8 meters per second squared if solved. All right, what do I have? What am I solving for? What's missing? What equation should I use? Plug in your numbers and solve appropriately. Last, I believe is the last one. A car accelerates at a constant rate from 15 meters per second, that says, to 25 meters per second while it travels 125 meters. How long does this motion take? How long does this motion take? All right. So this one is using the one equation that it doesn't come up too often in AP physics. Okay. We're solving for t, missing a. We have initial and final velocity and distance. I'm going to use the 1 half vf plus vi times t formula. Again, that's basically the average velocity formula. Okay. And so if I plug everything in and solve, time will come out to 6.25 seconds. Okay. Oh, there's another one. All right. A plane traveling 100 meters per second needs to slow to rest on a runway with an acceleration of negative 6 meters per second. How long does the runway have to be? All right. So this one, actually, I'm glad we got this one in too. We have initial velocity is 100, final velocity is 0. Okay, so we don't always go from low to high speed. It can go from high to low speed. And you can see we have a negative acceleration. We need to keep that all in there. We're looking for how long the runway will be. So we have initial and final velocity. Acceleration is negative 6. Okay. Solve for d, solve for x, missing t. All right, we're going to use the VF squared formula. This formula is often one that I see students go, oh, I don't like that formula. It has squares in it. We got to get over that. Okay, it's really not that difficult. All right, plug the numbers in appropriately, go. This is actually an extremely useful formula. We're going to be using it quite a bit to help solve some projectile problems very, very quickly. Okay. One other thing I'll quickly say. You can solve for anything before I finish this problem. As long as you have 3 of 5 variables, you can solve. Okay? So if you do happen to run into that problem where you're going, I only see two numbers, I only see 2 things. Obviously pay attention again, as always, to the word rest, because that means something is 0, either initial or final velocity. All right? But if you don't, even if that's the case, then it's a bad problem. You're not going to be able to solve. Okay? You have to have at least 3 variables in the problem. All right, plug it on in. 0 squared equals 100 squared plus 2 times negative 6 times d. And your distance for the runway would be 833 meters.
At this time, we are in a code blue.
830.
Again, staff, we are in a code blue.
So that's it. So that's what we're starting with for right now. Again, there's going to be a follow-up video pretty quickly of just some more problems being done. And then we'll also solve for free fall. So that's the introduction to the kinematic, very useful kinematic formulas. All right, thank you.